All right, now we're going to discuss a class of dynamical systems, primarily coming from Lagrangian Hamiltonian mechanics. And the motivation for doing this is to consider it's like a setting. It's like where certain types of geometric structure are preserved, and then go towards discussing how one constructs numerical methods which respect and preserve those conserved properties. Okay, so this is about Lagrangian and Hamiltonian mechanics. Okay, so you're given what is called a Lagrangian. Okay, L, which is a map from the tangent bundle to a configuration manifold Q. And in local coordinates, this typically has the form position and velocity. Okay, and this is a map from, again, the tangent bundle to Q to the rails. Okay, so it's a rail, so a scale valued function. It's like on the tangent bundle, and we sort of obtain what is called an action integral. Okay, so this is what's called a functional. It's something which takes a function, which in this case is a curve, and then gives you a number. Okay, so this is the action S, and it depends on some parametrized curve Q. And the action is the integral from some initial time, say t0, to a final time t1, of the Lagrangian evaluated on the curve Q as a function of t, and then the derivative of the curve Q dot, again as a function of t, and then you integrate this over time. Okay, so given the Lagrangian, you get this action integral, and then from that, it's like you can introduce what is known as Hamilton's principle. Then Hamilton's principle states that the sort of actual trajectory that the system takes, okay, satisfies the following principle. So that I guess I should say that you have a trajectory. It's like, and you have to first specify the boundary conditions. So states that the actual trajectory Q, okay, with boundary conditions Q at t0 is Q0, and Q at t1 is Q1. Okay, satisfies the following property, that the variation of the action integral, which I denoted by S of Q, right, is equal to 0, where the variations, or what is often referred to as the infinitesimal variations, delta Q at t0 is equal to delta Q at t1 is equal to 0. So the variations vanish at the n times, if you will. Okay, so you might ask, what do I really mean when I say delta of S of Q is equal to 0? All right, so let's try to understand that. So the basic idea behind this is that, so let me sort of draw a picture for you. So what you have is you have some configuration manifold Q, and you have an initial point q0 and a final point q1, all right? And then you look at, you're trying to describe a curve which starts at q0 and goes to q1. It's like starting at time t0 and going to time t1, okay? And then the actual curve which the system follows is that where if you were to vary the curve slightly, which is to say that you sort of perturb the curve while keeping the endpoints fixed, then to first order in this variation of the curve, the action integral doesn't change. So what do we really mean by that? Okay, so you introduce what are called variations. Okay, so variations basically are sort of a two-parameter family of curves. Okay, sort of, well, let me rephrase it. It's a one-parameter family of curves. So you have q epsilon. Okay, so epsilon is this parameter, and then you have something which depends on time. All right, and it has the property that so you take variations of the curve. Let's say q of t. Okay, so you have this original curve which we call q of t, and then we consider variation q epsilon of t, which is a parametrized family of curves with the property that q, where epsilon is equal to 0, right, is just the original curve itself. So when epsilon equals to 0, you recover the original curve, and then as epsilon varies, it's like so you vary smoothly away from this initial curve q0. Okay. And then in Hamilton's principle, in addition to this property that when epsilon is equal to 0, this variation, it's like recovers the original curve, you also have the property that the variations keep the endpoints fixed, right? So in Hamilton's principle, right, this q epsilon of t variation keeps the endpoints fixed. Okay, so what you mean by that then is that q for any epsilon at t0 is just q0, which is the left boundary condition, and then q for any epsilon at t1 is q1. Okay, so these are the family, again, this parametrized family of variations. It's like which you want the action integral to be stationary to. So it has to be that this family of curves, it's like recovers the original curve when epsilon equals to 0. And in addition, it's like when you evaluate at the endpoints, it's like the endpoints stay fixed. Okay, so with this variation, you can introduce two things. You can introduce what is called an infinitesimal variation. Okay, and what do we mean by that? Okay, so we denote this by delta of q at t. Okay, and this is really nothing more than the partial derivative with respect to epsilon evaluated at epsilon equals to 0 of q epsilon of t. So more or less what this is that it's the vector field, right, along this curve which locally generates this parametric family of variations. Okay. All right, so another way to sort of think about it is that you keep t fixed, you let epsilon vary, it's like, and then you compute the derivative with respect to epsilon, which is exactly what you have here. Okay, all right, so if you have an infinitesimal variation, right, then the fixed endpoint conditions mean that infinitesimal variation at the endpoints vanishes. So in particular, right, delta q at t0 is the partial of q epsilon at t0, right, which is the partial of a constant, partial derivative of this constant, which is q0, so that vanishes. And the same is true that the variation at t1, the infinitesimal variation at t1 is equal to 0. Okay, so once you have this idea of variations and this idea of infinitesimal variations, then we can start talking about what the variation of the action integral is. So when I say that the variation of S evaluated at Q, what I mean is that I look at variations of Q in this sense, all right, and then So I look at the integral basically from t0 to t1 of L evaluated on q epsilon t, q dot epsilon of t dt. All right, this is the action. So this is really nothing more than the action integral evaluated on q epsilon. Then I take the partial derivative with respect to epsilon of this thing. Right, this now is just some scalar valued function which depends on epsilon, and then I evaluate this partial derivative at epsilon equals to 0. So this is what I mean, if you will, this is the definition of the variation of the action integral. Okay, so once you have that, then we can start talking about what setting this variation equal to 0 implies. Okay. Okay, so you have that 0 is equal to the variation of SQ. All right, so this is defined to be the partial derivative evaluated epsilon equals to 0 of the integral from t0 to t1 of the Lagrangian evaluated on q epsilon of t, q dot epsilon of t dt. Okay, and then you can basically swap the integral and the derivative. In general, it's like when you do this, there will be a boundary term which shows up. But because the variations of q vanish at the endpoints, the boundary terms vanish. And so you can just swap the integral and the derivative. But again, in general, one has to be careful, and there is typically a boundary term. Okay, so what you get then is an integral from t0 to t1, and this partial respect to epsilon of this integrand, which is the Lagrangian. Okay, so you just get, you just apply the chain rule, you get dl dq, and then you get a dq epsilon, the epsilon evaluated epsilon equals to 0, which is of course nothing more than this infinitesimal variation, which I denote by delta q. Okay, then you do the same thing, you get a dl dq dot, and then there's a something like this, right, which is the very sort of the partial derivative with respect to epsilon of the time derivative of the sort of variation. Okay, then again evaluate epsilon equals to 0. Okay, so technically this is something like the variation of delta q. And then what happens is that by the equality of mixed partials, the variation of delta q is equal to the time derivative of the variation of q. Okay, and then again the whole thing is integrated with respect to dt. So let me just write this down. It's like in a slightly simpler form, right? So you get dl dq variation of q plus dl dq dot, right, ddt variation of q, the whole thing integrated with respect to time. Okay, so the next thing you want to do is you want to do an integration by parts, and the reason why you want to do an integration by parts is you want to take the time derivative of the variation of q and put it onto this dl dq dot term, so let's do that. Okay, and again it's like the boundary term vanishes because dq, it's like the infinitesimal variation of q, it's like at the endpoints t0 and t1 vanish. Okay, so going from here to here, there's an integration by parts. And again, the boundary term vanishes because the variation of q vanishes. So you get t0, t1, dl, dq, and I'm going to take the delta q out now. Okay, so minus d dt, dl, dq dot. Okay, and there, this is now paired with the variation in q, and then there's an integral dt. Okay, so maybe I should just add the boundary terms. So this integral, well, not integral. Okay, so the boundary term is dl dq dot, right, delta q t0 t1, and this goes to 0 since delta q at t0 equals to delta q at t1 is equal to 0. Okay, all right. So you have now this condition that 0 is equal to this integral of something paired with a variation delta q and then integrated over delta t. All right. So what can you do? So the point basically is that the idea is that if you choose, these families of sort of varied curves, right, these variations in a smart way, then more or less what you can do is that you can imagine, again, having this reference curve q of t, and you could imagine having q epsilon of t be such that it's the same as q of t everywhere except for a very small region about a given point. And then you allow, as epsilon goes to 0 to vary. And then you can concentrate this variation so that all the variation is more or less localized to some very small neighborhood of a single point. So more or less the idea is the following, that if it's the case that this thing is equal to 0 for any variation which keeps the endpoints fixed, then by allowing you to choose these variations so that they are localized, what has to be is that this thing in the parentheses has to vanish as well. Okay, so more or less it's like this is the statement of the fundamental theorem of the calculus of variations, right? That so by the fundamental theorem of the calculus of variations, okay, what basically happens is that in order for this, again, integral, it's like to vanish for all variations which keep the endpoints fixed, this thing in the parentheses has to vanish pointwise. Okay, so we have that, dl dq minus d dt dl dq dot is equal to 0. And then obviously the converse is also true. If this is 0 pointwise, then clearly this integral vanishes as well, right? So again, the point of the fundamental theorem of the calculus of variations is that these two things are equivalent. Okay, so these equations here, it's like dl dq, it's like minus d dt dl dq dot is equal to 0, is then what is called the Euler-Lagrange equations. Okay, this is a very nice coordinate-independent way of describing, amongst other things, Newton's second law. So the basic idea is that when you describe Hamilton's principle in the sense of variations of curves and its impact on the action integral, nowhere it's like in this sort of abstract description of Hamilton's principle do we appeal to a specific choice of coordinates. So the basic idea, if you will, is that the resulting stationarity conditions, the resulting Euler-Lagrange equations, hold true irrespective of how you've chosen to frame the problem in terms of coordinates. So let me sort of illustrate now. It's like how the Euler-Lagrange equations are related to Newton's second law. Okay, so that involves choosing a specific choice of Lagrangian. Okay, so let's look at an example. Okay, so let's say you have a Lagrangian, which is the folding form. Lagrangian depends on position and velocity. So let's say half q dot transpose m q dot. So this is a kinetic energy type term minus v of q. So this is kinetic energy. And then this is v is the potential energy. Okay, so you have a Lagrangian sort of form kinetic minus potential. All right, so let's see what happens. Right, the Euler-Lagrange equations of the form, it's like dl dq minus d dt dl dq dot is equal to 0. All right, or if you prefer, it's like you can obviously write this as d dt dl dq dot is equal to dl dq. All right, so let's look at what happens when you have this Lagrangian. So dl dq dot is nothing more than m times q dot, right? So this is really the momentum. Okay, and we'll see it's like when we talk about Hamiltonian mechanics that this is oftentimes denoted as p, which is the usual notation for referring to the momentum. Okay, so this is saying then the time rate of change of the momentum is equal to dl dq, which is minus the gradient with respect to q of the potential function evaluated to q. So this is really a statement of Newton's second law that the time rate of change of momentum is equal to the external, or to the force it's like which is generated by the potential, right? So this is a statement of Newton's second law. All right, so that's really sort of a quick and dirty introduction to what is called Lagrangian mechanics. And then traditionally, Lagrangian mechanics is formulated in terms of this variational principle. And then we're going to look at Hamiltonian mechanics, which is oftentimes described in terms of either the symplectic or the Poisson structure. But we can also see that there's also an equivalent variational formulation for it. So we'll see that in a little bit.